Hello, everyone. Uh, my name is Corey Pye, and I'm going to be talking to you today about computational chemistry applied to solutions, in particular, how I apply this to the study of anions. Predicting the properties of electrolyte solutions often requires an understanding of the hydration of ions in aqueous solution. It is known from solution diffraction data that water molecules near an ion can be differentiated into hydration shells. And this inner hydration shell of metal ions, for example, can give rise to vibrational modes, which can be assigned by Raman spectroscopy and ab initio calculations to the aqua ions. For example, magnesium shows a band at 358 wave numbers in the Raman, and which is assigned to the totally symmetric stretching motion of the hexa-aqua magnesium ion. Now, anions, they tend to be less affected by this, but the vibrational modes themselves of the anion can be significantly altered by the solvent. In this case, we're going to be focusing on water. And in this poster, we'll be focusing on the hydrogen arsenate ion. The arsenate ion has TD symmetry in aqueous solution, and it has a 3- charge and chemical formula ASO4 3-. If we look at the vibrational modes, there are 4 modes that are observable. There is the A1 mode, which is observed in the Raman spectra, and it's also a polarized mode. There is also an E mode, which also appears in the Raman spectra, but it's depolarized. And then there are also 2 T2 modes. They're observed both in the infrared and the Raman, and in the Raman spectrum, they are depolarized. They appear at 794 wave numbers for the A1 mode. This is the totally symmetric stretching mode. The new 3 mode, which is of T2 symmetry, appears at 814 centimeters to the -1. This is the asymmetric stretching mode, or the degenerate stretching mode, if you prefer. There's also 2 deformation modes of E and T2 symmetry, which appear at 350 wave numbers and 405 wave numbers. Now, when you protonate the arsenate ion, you get the hydrogen arsenate ion, and the symmetry of this particular species at most can be C3 if your hydrogen was pointing directly away from the arsenic atom. But of course, in practice, that doesn't happen. It's actually lower. But you can imagine that in the limit of fast proton exchange, or in fast rotation, that you might have an effective C3V symmetry if you treat the OH group as a simple point mass. And when you do that, you're going to see 3 A1 modes and 3 E modes, not including the 3 modes that are missing because of the treating of the OH as a point mass. Those 3 modes would be the oxygen-hydrogen stretch, the hydrogen-oxygen arsenic bend, and the OH rotational motion, the torsion. If the symmetry is lower still, for example, CS, you should see 8 A prime modes and 4 A double prime modes, which should have different, should be differentiable based on their depolarization ratio. And then, of course, if there's no symmetry, all the modes would be polarized. Now, in C3V, if you make that point charge approximation, then these modes of hydrogen arsenate can be assigned at 315, which is a deformation mode corresponding to E. There's a mode at 327, which has been assigned to the A1 component of the T2 mode, and also a mode at 380, which is the other component. Protonation will weaken the arsenic-oxygen bond, and so that will appear at lower frequency at 707 wave numbers. There's also going to be the other degenerate stretching modes, which now split into an A1 and an E mode, which appear at 838 and 866. And then, of course, the bending mode of the hydrogen oxygen arsenic bend is appearing at 1170. The twisting motion is not observed in the solution spectra. So what we did, we used the programs Gaussian 98 and Gaussian 03. We performed sequential optimization of these structures. We looked at using the Hartree-Fock STO3G and 321G basis sets to start, followed by 631G star and 631 plus G star. And then we finished up our calculations with the MP2 calculations using the frozen core approximation at the same two split valence polarized and split valence polarized plus diffuse function basis sets. We use Z matrix coordinates to symmetry constrain our molecules. And very early on, we dropped the Hartree-Fock STO3G calculations because the hydrogen bonding was predicted to be very asymmetric. Essentially, what happened was the water molecules lost one of the hydrogen bonds, and whereas this didn't happen at the better levels. We also did not apply any frequency scaling. We didn't use any solvation models. We did not do any Boltzmann averaging, and we didn't add polarization functions on hydrogen. The reasons for this was explained were explained in the in our paper on hydrogen sulfate hydration. So what we found is that in general, for the naked hydrogen arsenate ion, the cis form is actually lower than the trans form by between 4 and 11 kilojoules per mole, depending on the level of theory. We also found that the arsenic oxygen bond distance for the protonated oxygen was longer than the arsenic oxygen bond distances in the non-protonated distances by around 0.2 angstroms. When we add a single water molecule, this can interact with hydrogen arsenate in one of 4 possible ways, typically. The water can be a double donor to both oxygens where these are not containing a hydrogen bonded to them. A second option is a donor-donor acceptor water, where the water molecule donates to 2 oxygens as above, but also accepts the hydrogen from the OH a part of the hydrogen arsenate molecule. A water could also potentially interact with the oxygen not containing hydrogen and also an oxygen containing a hydrogen. And then finally, the water molecule could be both a donor and an acceptor, donating to an oxygen not containing hydrogen and accepting a hydrogen bond from the OH part of the arsenic molecule. And usually the DDOO form is the most stable of these possibilities. At two of these levels, the Hartree-Fock 321G and MP2631G star, the DDA type water molecules are the second most stable, but these are usually less favored at other levels. And then attempts to actually make DA type water molecules often result in a proton transfer to give a hydrogen bonded interaction between a hydroxide and the dihydrogen arsenate ion. So these structures are much less stable than the other forms. So if we look at the bond lengths, we can see that the MP2 bond lengths are a little bit larger than the Hartree-Fock bond lengths, which makes sense because this is a correlated method. The 321G bond lengths aren't that bad at all compared to the these better basis sets at the Hartree-Fock level, but the STO3G bond lengths are a little too long, especially for the arsenic oxygen where they're not having a hydrogen attached to them. Now, when we actually take this naked hydrogen arsenate ion, calculate the vibrational frequencies, we can kind of see here that if we compare it to experiment, which is given over here, the Hartree-Fock calculations that these better basis sets are not too bad right here. They're a little bit too high right here. And they are a little bit too high for the stretching motions as well. This is a well-known feature of Hartree-Fock method, having a slightly higher frequency than experiment. But the deformation modes are actually not bad, especially for the E. If we look at the MP2 results, we can kind of see that the stretching frequencies are a little bit better, which is well known. But then the deformation frequencies, this one here especially, is a little too low. In all cases, the ASOH stretching frequency, so this is the arsenic oxygen with the hydrogen attached stretching motion, is always too low compared to experiment. Remembering that this is a naked hydrogen arsenate ion. And so we postulate that this is due to the neglect of hydration of this ion at this point. So we decided to hydrate our ions. So when we look at the hydrogen arsenate ion, which looks like this, we can see that this is the form that's preferred, the cis form. The hydrogen here is cis to one of the oxygens. In this case, it's trans to the oxygen. This is a little higher in energy. When we have our water binding to it, this is our double donor to the OO. This is an O without a hydrogen and an O without a hydrogen. This is a donor-donor acceptor type interaction. You can kind of see here there's a weak interaction between the this hydrogen and the oxygen interaction here. This is another type of DDOO interaction, which is asymmetric. These refer to the symmetry. Here is a DDOHO, so it's a donor to an oxygen, which doesn't have a hydrogen to it, and it's also a donor to an oxygen that does have a hydrogen on it. So this is the DDOHO. Attempts to generate the DA species result in a proton transfer. You can see this is the original water molecule where one of the protons has been transferred to the hydrogen arsenate to give the H2ASO4. Of course, the STO3G basis sets tend to give asymmetric hydration such as this, where only a single hydrogen bond will exist, the other one breaks, and so we drop this level fairly on, as I indicated. As you add more and more water molecules, there's a multitude of possibilities for 2 water molecules. Of course, when you have 2 water molecules, there is a possibility of hydrogen bonding between the water molecules and not between the water molecule and the hydrogen arsenate. In some cases, you do see the this OH minus and the H2ASO4 ion being hydrated here. So there are some examples here. In this case, you have a hydrogen bond between the water molecules, although in this case, these structures tend to be less favored than where they're interacting more directly with the ions, possibly because of the 2- charge. In something like hydrogen sulfate ion, the water-water interactions are a little more strong than the water-hydrogen sulfate interactions, and so they tend to predominate. But for hydrogen arsenate, it prefers to solvate the higher charge. When you go to 3 water molecules, you see again more possibilities, and then eventually the number of possibilities tend to reduce a bit once you get to 4, 5, and 6 water molecules. So for 6 water molecules, this is what we observe here. So this is as high as we go for the hydration. When you calculate the vibrational frequencies, you can kind of see that we have our E mode right here. So this is a doubly degenerate mode. The twisting mode sometimes gets mixed up in here as well. Here you have your deformation mode, which is also normally T2 mode. So the calculations are predicting that there's not that much of a splitting between the A1 and the E modes, which formerly corresponded to the T2 mode of arsenate. Here we have the arsenic OH stretching mode, which is much lower in frequency than the arsenic oxygen stretching modes of the other 3 oxygens. So of course this is much weaker than these. This is the deformation mode of the OHAS bending. So this is higher in frequency. For something like hydrogen sulfate, this mode is either lower or higher than these stretching modes. It tends to be mixed up with them quite a bit, but in this case you have a clear differentiation between these oxygen arsenic stretching modes and the deformation or the bending mode. As you go to more and more waters of hydration, you have a clear change here. So this is with 3 water molecules, the same pattern for all the different structures. You have a variation within each structure, but they appear roughly the same frequencies as a group. For 4 water molecules, and then for 5 and 6 water molecules. These are right here. So what happens when we look at our vibrational modes? There's a slight increase of the deformation mode. Actually, both sets of deformation modes, there's a slight increase in frequency. There's a much larger increase of frequency due to the arsenic OH stretching motion. There's only a slight change in the ASO stretching modes that are of higher frequency. And then there's actually a fairly big change in the deformation mode of the arsenic OH bend. So hydration affects mostly the ASOH stretching mode and the ASOH bending mode. So the conclusions of this study is that we slightly reassigned the A1 deformation component. Up here, we think this is actually something else. If you look at the standard deviations of all of these structures, you can kind of see that these have a fairly broad width associated with them. If we take the maximum value of these numbers here, these are, if you multiply these numbers by 2, you get an approximate estimate of the full width at half height of the bands that they correspond to. And so we also think that because of hydration, water becomes less and less effective at hydrating ions at higher temperatures. And therefore, at lower temperatures, the arsenate ions should be matching more the multiply hydrated vibrational frequencies, whereas at higher temperatures, it should be matching more closely to the unhydrated system. So what this means is that at higher temperatures, the vibrational frequency of the ASOH mode should decrease quite a bit. This effect has been observed in hydrogen sulfate by Wolfram Rudolph in 1996. And so we think that this arsenic mode will also exhibit the same properties. So that's a prediction that's coming from this study. Also, we think that this deformation mode, which is a lot harder to observe, should also be decreased in frequency as you increase the temperature, if it's ever able to be observed. And thank you for your attention.